about creating a precipitate. Okay? So this kind of goes in with common ion, I guess, but we can create precipitates because the whole point of this, right, is that some things are soluble, some are not. The degree of solubility affects how much is going to dissolve. Well, if it's not dissolved, what is it? It's a precipitate. It's settled at the bottom, right? So creating a precipitate. We know what precipitate happens when you add two aqueous solutions together and you end up with a new solid, right? This solid that you make has to do with KSP. So everything is kind of like all tied together, right? So precipitation, if two aqueous solutions are mixed and produce a new solid, right? This guy, this is called the precipitate. Okay, now there's going to be other ions in the solution as well. Okay, and those ones are going to be saturated essentially. Any other solution in the beaker is saturated. Okay, because there's still ions in there. Now we're going to do some examples so you can kind of see and think about what's going on in that beaker. Okay, so adding, I've got lead nitrate and sodium iodide solutions. Okay, now both of these are completely soluble according to my solubility rules. However, if I write out this equation, so this is what I'm going to do, I'm going to write the equation. Okay, if I put lead nitrate, NO3, this is aqueous, with sodium iodide, okay, also aqueous, I make, this is double replacement, right? So I'm going to switch my ions. So now Na is going to be with NO3. If I check my charges, that's what I got. And then Pb is going to be with I, and it's 2 charge. Now, if I check my solubility rules, this is the one that's not very soluble. Okay, anything with sodium or nitrate is completely soluble. This is not balanced, so I need a 2 here and a 2 here. This is the molecular equation for the double replacement reaction that happens when I add these together. It actually makes a bright yellow solid, and that is lead iodide. Okay, now if I were to write the net ionic equation, right, the net ionic equation shows what just makes the solid, right? It's Pb2 plus aqueous and 2I minus aqueous makes PbI2 solid. That was what created the solid. So this is the net ionic equation. Okay. What did we leave out? Well, we left out those spectator ions, the NaNO3. They don't actually participate in the chemistry at all. They're just floating around in there. They're there. Okay. This net ionic equation is going to be important. Now, if you look at this, hopefully you noticed this is essentially the reverse of a dissociation equation, right? So this is where KSP is going to kind of play in. Now, very much like titrations, anytime we make a precipitation, we're going to have to do a BCA table and a KSP equation, just like a titration. So BCA and then equilibrium stuff. Okay, so we have to take into account that there's stoichiometry that goes on. We make some stuff. How much should we make? And then there's some leftover stuff. And then what's going on with the equilibrium. All right, so these are kind of our strategies. All right, the first one tells us how much solid we make. Okay, so how much precipitate. Okay, right, I did this equation, this lead and iodide made PbI2, right? And then the second part, we need like essentially what's left over. And we're going to look at that equilibrium. Okay, so we're going to do example number 5 here together. I know this is a lot of numbers, so we really got to break it down. Okay, I'm using the same compounds that I have up here. So I'm using this equation. All right, so I've got 45 milliliters of 0.05 molar lead nitrate. I added 75 milliliters of 0.08 molar sodium iodide. Okay, so I just have the concentrations and the molarity. So if I have concentration and molarity of each one, I can find the number of moles that I added, right? Now, again, hardly ever is it going to be a perfect ratio. I'm probably not adding, if I have my lead part, I'm probably not adding exactly twice as many moles of iodine. Most likely not. So we're going to have a leftover one, and that's going to affect our solubility and stuff. So I've got moles, so I can do a BCA table, no problem. Okay. Resulting in a precipitate of PbI2. Okay, that was this guy. So that's what happens. If the KSP for this compound is this value, it's not very soluble, right? This makes it solid. Then what is the concentration of both ions at equilibrium? Okay, so I mixed some stuff. I made a precipitate. So I'm going to have to do BCA and then KSP. So BCA might be the easier one right now to think about. Always do the BCA first. So What I want you to use is the equation that made the solid. Use the net ionic equation, otherwise it's going to throw off your stuff later. Okay, makes PBI2. Okay, so I'm going to write up here, always use your net ionic for the solid. Okay, so this is what I did equation-wise, right? So I'm going to go B, C, A. If I multiply this and this, well, that's divided by 1,000. The number of lead ions I had, my moles here were 0.00225. If I multiply this and this, I get my iodine ions. So I started with 0.006, and this is a solid, so whatever. These are going to make the solid, so I'm going to lose this, minus 2x. Also, these are reactants, usually negative. So I get 0.00225 minus x and 0.006 minus 2x. Okay, now if I look at these, I need to figure out which one is going to be my limiting reactant. One of them I'm going to run out of and make as much solid as possible, and the other one I'm not. So you might be able to tell by looking at this if I have enough iodine or whatnot. Essentially, I need twice as much iodine as I do lead because it's a 1-to-2 ratio. So I'm going to run out of this because I have twice as much iodine. If I double this, I need what, 5.5 or 0.0055, which I do have of the iodine. That means this one is going to be my limiting reactant. This one I'm going to run out of. Now, if you can't tell, just set one of them equal to 0 to solve for x. Okay, so that's what I'm going to do. I'm going to set this one equal to 0.00225 minus x equals 0. So x is 0.00225. Okay. If you end up, then when you plug x back in, if you get something negative over here, that's impossible. So you picked the wrong one, then set the other one equal to x. But this is going to work. So I solve for my x. So I put that back in. So 0.006 minus 2 times 0.00225 means I have 0.0015 moles of iodine left over. Okay, this was the important thing I needed to get from the ice table, right? All the lead was used to make solid. I made as much solid as I could, and now there's some iodine left over in there. Okay, so step 2 is doing the KSP part, okay? So for this lead iodide, so I'm going to write the KSP equation or the dissociation equation, okay? Got PB 2 plus and 2I minus, so aqueous. Okay, these hopefully will be easy to remember because they're always opposite of each other. The BCA one is making the solid, and the dissociation one is breaking down the solid. So this one, you made the solid, this one is my ice, and I'm going to use my dissociation equation. So this is solid, I don't care. And now this iodine is what I'm going to have to put air in my initial. It's like a common ion type situation. Okay, now ice has to be in molarity though, so I do have to put it over the total volume. Let's see, so it's this many moles, so the iodine molarity is going to be 0.0015 moles over, let's see how many liters we have. I have 75 milliliters and 45 milliliters, which I need to add together, so I would be 0.045 plus 0.075 liters. This concentration ends up being 0.0125. So that's what goes here, 0.0125. Okay, now I ran out of the lead, there wasn't any lead. Okay, so I'm going to do this just like a regular KSP. This is plus x, this is plus 2x, this is x, this is 0.0125 plus 2x. All right, let's see, what am I even looking for here? I have the KSP, so I can solve for x, and I want to know what it says, what is the concentration of both ions at equilibrium? So that means I want to know the lead and the I. So I want these two values. All right. So I'm kind of running out of room here. So I'm going to move this really quick. Hang on. Oh, okay. So I just moved that down here. I'm right here. I have KSP from the problem is 9.8 times 10 to the negative 9th. That is going to be this times this squared. Okay, so x times 0.0125 plus 2x squared. And then I need to solve for x, all right? Use your solver or drop the plus 2x, however you would like to do it. I get x is 6.2 times 10 to the negative 5th. Okay, now what was the question asking for? It wanted the iodine and lead concentrations at equilibrium. So X is lead. So the lead 2 plus concentration is 6.2 times 10 to the negative fifth. And the iodine concentration is 0.0125 plus 2X. So you can plug that in. It's essentially about the same as it was to begin with. 2 sig fig wise is 0.013, or you could have written 0.0125. These are both molar. Okay, so these are the answers, right? I know it's a lot of work, but just like titrations, you're going to do BCA to make your solid and then ice for your KSP equilibrium.